Okay, and a formal good morning to everyone. Math 70, spring 2003. And Debbie, I know we were listening to Rod Stewart, and I wasn't listening carefully enough when it first started, and then it got quiet. So what was it we were listening to? Maggie May. So nice eternal youth of Rod Stewart. I think he's been around nearly as long as Algebra. Not quite that long, but close to it. You had some homework last night, and one of the principal things I ask you to do really doesn't get structured in a particular problem that you do, but that was to memorize the 11 properties of the real number system. So let's see what you can do in 30 seconds with a blank sheet of paper. This is not to be turned in, but this is to see how good your recall is 24 hours later. Well, 23, because it was near the end of the hour. But I'd like you to try writing down the 11 properties of the real number system. If nothing else, the 6 categories. There were 2 in each of 5, and then 1 by itself. So these are categories. Nothing else, the categories. And that shouldn't take you too long for the categories. And then, of course, there's the question of notation that goes with it. So while you're doing that, I'm going to wander around and see how marvelous we are doing. Once you get the categories, and that's sort of the key to this, get categories first, then start filling in the notation that goes with this. So categories first. There should be a total of 11 properties. Now we've spent better than 20 seconds. You should have at least listed the categories at this point. Okay, and you can expect something like this in the first exam. Okay, so we are having marginal success with the categories. And then once we've had the marginal success with the categories, there is some notation I'm seeing, so that's good. Okay, and again, I just want to walk around and look at what you're doing. This is a rather important piece of information that you need to have as part of your background. Okay, now that's been about 1 minute that you've had to write those down at this point, and that is a concern that we be able to do this exercise in a reasonably short period of time. If you have them cold, you should be able to write 11 categories probably in 20 seconds. And then another maybe, let's say 80 seconds, 5 seconds for each one for notation if you really have it cold without pushing yourself. And it suggests that we aren't there. Okay, so the question, let's see if we can summarize those again. We have closure. What does closure say again? In verbal way. Just a verbal explanation for closure. If you start with 2 numbers in the real number system, A and B, and you add them together, what are you guaranteed? A real number. So you'd say A and B are part of R, where R stands for the real numbers. And we have then A plus B belongs to R. Now what's the symbol for belongs to, contained in? Sort of a, well, you think of it as C with a cross, and it looks a little bit like an E, but we would be saying A plus B is contained in R. That's our closure. That's closure for what? Addition. So if we think now in terms of multiplication, what would we say? AB, meaning A times B, is contained in R. So if I come back to my expression here, AB contained in R. Now, position is important in mathematics. More precisely, juxtaposition. When 2 letters are written next to each other, the implication is you will multiply. Now, that becomes rather important in terms of exponents. So just as an aside, if I have an a letter like A, and I put the 2 above it, what we call a superscript, that means you have a to the second, A squared, A times A. But as you're going to find, if I write the 2 as a subscript, that suggests I have 2 different A's, A sub 1 and A sub 2. That's like an X and a Y. But in many areas, such as statistics, we use a single letter to represent 20 or 30 different values, and we then use a subscript to indicate which value we're referencing. So you'd have A sub 1, A sub 2, A sub 3, and so on. If I put the 2 in front of the A, that tells me what? I'm going to multiply 2 times A. Where you write symbols becomes very important as to how you interpret what is written. In that sense, algebra, a kind of symbolic language for mathematics, is very detailed and does not allow for sloppiness. So if you put a 2 down here, you mean something very different. And if you put the 2 in front, that means something very different. Okay? This would be awkward. Why? Well, you aren't sure if it's a superscript or a subscript, but what's awkward about it if you intend it to be 2 times A? What is our general rule of thumb? The number would be in front, the letter after, the letter follows, because there is a lot of question as to what's intended here. With all due respect to Lucas. R2D2? Okay, so there is sometimes in literature room for A2, but that's more in Latin. Brutus? Okay, well, it's a slow morning. The fog's up. Closure. Okay, so we had closure. Now, after closure, it's not perhaps clear what we should do next. Perhaps we should go to the end at this point, and the last one, at least, sort of fills in the gaps in between then as our goal, the distributive property. What did that say? Did you get that one down? It's the only one that involves multiplication and addition together. So we have a separate property here in closure for addition and multiplication. The distributive takes 2 things and puts them together in one property. How do you verbalize it? With A, B, and C.
A.
Boy, that's really quiet. I mean, hardly discernible.
A times B plus C equals...
Okay, now if we say A times B plus C, don't we have to some way tell the listener where the parentheses are? And it's awkward to say A, open parentheses, B plus C, close parentheses. How do we say it instead?
A, the sum multiplied by the sum of B plus C.
Good. Or the quantity B plus C. Now notice we have to start creating a language. A sum. And you need to know what sum means. Now that's S-U-M. It's the result of an addition. If you have a subtraction, what do you call the answer? The difference. Good. And if you have multiplication, you call the answer a product. And if you have a division, the answer is called quotient. So sum, difference, product, and quotient, words that must be part of your vocabulary. Now, what will make algebra easier is learning the jargon. You need to know what those words mean, or as you listen to what we say, it will not make sense. And then you will not be able to be articulate. So when we want to say that we have A times the sum of B plus C, then it becomes much clearer that I mean this expression. So this product, which you interpret as a multiplication, results in the sum of two products. The language very, very carefully stated. So that tells you that you're going to have AB plus AC. You distribute the A over this sum, getting two products, which you then add together. That is the essence of what we call factoring, which we're going to talk about this morning. Products mean you multiply. The two things you multiply together are called the factors. So, as we talked about this yesterday, and said we had something like 2 times 3, 2 and 3 are the factors. The answer, which is 6, is the product. Now, it's rather interesting. In the English language, if you just listen to people, you realize how we aren't very exact. If you go out to the student center and listen to people talk, sometimes you need a translator. Okay, but aside from that, we aren't very articulate. We aren't very precise. And in mathematics, in algebra, you have to be very careful of what you say and use the right language. I find it as I go to places and talk with people in social settings or just in the business community. One of the observations has to do with the precision, the careful use of language, and it catches people by surprise because they aren't typically involved with carefully, precisely stated phrases. Most of what we tend to say could be cataloged under, we'll fill in the blank. Now, we have 3 out of the 11. What am I missing? Anybody? The commutative, which says that you can do what? Just a verbal statement. Flip-flop. I like that. 2 plus 3, 3 plus 2. Flip-flop it, you get the same answer. 2 times 3, 3 times 2. Same answer. Commutativity. Commute back and forth. What's another one? Associative. What's the essence of associative? Okay, that's one way of saying it. Order stays the same, the grouping changes, but what does it imply to you if you are adding 3 numbers?
Oh, you group them in.
It doesn't matter which 2 you start with, you're still going to get the same answer. So you can sort of slide the parentheses going backwards or forwards. Commutativity, associativity. Now what else? Identity. What is the identity?
A.
Say that again, Laura.
If you add a 0 to a non-zero number.
I can't add 0 to 0?
No, that's not what I said. I thought.
Okay, go ahead. Let's try that again.
I think what I meant was if you add a non-zero number.
Why does it have to be
If you have a
non-zero?
non-zero number, I don't know. That's what it said in the.
That was for inverse.
Oh, okay.
Aha.
So if you have a number and you add 0 to it, it's still.
You get your number. You retain your identity. A plus 0, A. Okay, Laura, since you started this, what about the identity for multiplication?
If you multiply any number times 1, it still remains the same.
Good. A times 1 is A. Now the inverse, and that was where Laura was talking about A cannot be 0, because you're going to take the reciprocal of the number. So if I start with a 3, I get a 1/3. If I start with a 5, I get 1/5. If I start with 2/3, I get 3/2. You turn the number upside down in a sense. So if I start with a 3, that's really 3 over 1. So when I take the reciprocal, it is 1/3. So turn it upside down. We talked about flip-flop. Okay, now we turn things upside down. What's wrong with having 0 as part of that? Does the reciprocal of 0 exist?
No.
No, it's undefined.
We're saying, could you have 1 over 0? The answer is no. It's undefined. How do you check a division problem, just a reminder? you do the inverse multiplication. So if you take 2 into 10, you say your answer is 5 because 5 times 2 is 10. Okay, take 0 into 1. Nothing that you can write down multiplied by 0 will give you that 1. Hence, undefined. An impossible operation. But there is an interesting question. Let's fast forward to calculus. A little bit of algebra, a little bit of calculus. Now, using Laura's statement, I can blame Laura on this. 1 over a. That was the reciprocal, correct? That's called the inverse for multiplication. Now, what is 1 over a as a gets small? And gets smaller and smaller and smaller. Let's try. A is 1/2. What is 1 over a? Whew. Okay, a is 1/2. I want to know what 1 over a is. What did we say 1 over a meant? We lost something in the translation there. What is 1 over 1/2? You make me pained. How about 2? 1 over 1/2 means 1 divided by 1/2. How many times will 1/2 go into 1? Whew. Yes, that hurts. 1 divided by 1/2. What do you do as a rule? Invert and multiply, in case you have forgotten. So we're going to invert and multiply, and I'm going to use x for the moment as an operation symbol. And 1 over 1 times 2 over 1 is 2. If taking the reciprocal means turning something upside down, and a is 1/2, then 1 over a is 2 over 1, which is 2. Now that little discussion is more serious than it seems. Because I'm now asking you to use the symbolism and the notation and understand what you're getting for an answer, and just knowing the words and not being able to do what I'm asking you to do right now is a little red flag saying, watch out. Let's try a different question. If a is 1/3, where am I going to write that? Let's try this. A is 1/3. What is 1 over a? Okay, 2 people are with me now. 1 over a, if a is 1/3, 1 over a. Good. One more time. If a is 1/3, 1 over a is?
3.
We're getting closer.
Equals
if
3.
a is 1/3, what is 1 over a?
3.
Better. Okay, a is 1 over 100. What is 1 over a?
100.
You
200.
regressed.
200.
1 over a is 100. A is 1 over 1 million. What is 1 over a?
1 million.
1 million.
1 million. Okay, now let's go back to my question. We have 1 over a. As a gets smaller and smaller and smaller, what happens to 1 over a? It gets
Bigger.
bigger and bigger and bigger. Is that making sense? What we just said in language is the following. If we look at the expression 1 over a and let a get smaller, that's what I mean by a limit. You all know what a limit means. Your mother or father at some point said to you, I've had it. I've reached my limit, which you interpret as you're in deep trouble. Okay? You're letting a get smaller and smaller and smaller and smaller. So that's what I'm expressing there in language. And that is at the heart of calculus. Now my point in this, and by the way, if you want to know the symbol for the number gets bigger and bigger and bigger, lazy 8, known as infinity. The smaller a gets, the bigger the quotient gets. Now, what's the whole point in that exercise? Sorry, Debbie, I didn't telegraph that well at all. The essence is language that you're learning in the second day of an algebra class, learning what an inverse is as a property of the real numbers becomes the heart of an expression that is necessary in a calculus class that we would be talking about in the first semester of a calculus. The language you learn here is critical. It's not just you take an algebra class and say, okay, I've had algebra. It's learning the language, the notation, and then being able to do something with that result. Okay? And you say, gee, why are you talking about that in here? Well, in Math 10, we start with talking about things like this. It's not unusual in the Math 10, the intro class, for me to talk about calculus. It's not like one course sits in isolation from another. Okay, that's all because of Laura. She said A not equal to 0. But A can get close to 0, and the closer it gets to 0, the larger 1 over A becomes. Okay, enough of the properties. You need to be able to say, verbalize, write, and understand all 11 properties of the real number system. It'll be on the first test. You should have known them from Math 20, a pre-algebra. If your pre-algebra background is lost in antiquity, however we define antiquity, 14 years, 22 years, or whatever, resurrect it, folks. Go back and dig it up. You're responsible for the content. Part of the notation that we talk about with the real numbers is implying you have some very good understanding of what a real number is. We talked about that lightly yesterday. I asked you to write a number. And in doing that, you very much convinced yourself in your basic response to that that you thought a number was a counting number. And I challenged that with a fraction. I challenged it with a decimal. And we talked about what particular real number in a decimal form from yesterday. Pi. In the usual form, most of you are familiar with it, is 3.14. But it is 3.14, 159, more garbage to come. Okay. A real number can be broken into two subgroups, subsets. A set is a collection. What are those two sets? Anybody? Give it a shot. Because pi was an example of one of the sets called an irrational. And then the other part is a rational. Now, what do we mean by a rational number and an irrational number? What's the root word to rational?
Ratio.
Ratio is a root word. Ratio. Rational. You just put an NAL after ratio. Ratio means a fraction. So a rational number is a number that can be written as a fraction. 2 over 3. That is a rational number. 2 by itself can be written as 2 over 1. So that's a rational number. Now when we say that we have a rational number, bless you, over to the right side of the board now, Debbie. If we have a rational, the argument is that P and Q are going to be integers, big I for integers, and Q not equal to 0, courtesy of Laura, and a rational number then would be P over Q. Hence, knowing your P's and Q's. P over Q, rational number. Q not equal to 0, P and Q integers. What's an integer? Give me another phrase for an integer. Anybody?
The -2, I don't know.
Okay, -2 is an integer. Give me another integer.
A whole number?
Whole numbers
And
are part of the integers. So a whole number like 5 would be an integer.
Plus
But
a-
-5 is also an integer, but not a whole number. Get the idea? So integers allow us to take the whole numbers and then put minus signs in front of them as inverses and take that together. So -3, +5, -4, 0, 18, 1,000,000, -3 billion. All integers. Now what do you think the phrase irrational means? Okay,
And the,
let me try this. You know what responsible means? What does irresponsible mean? The opposite of responsible. So if it's irrational, it means
the opposite of rational.
opposite of rational, which is not rational. Now you've heard it in terms of behavior. Rational and irrational behavior. Well, this is rational and irrational numbers. So real numbers can be broken into two categories, rational and irrational. Now another phrase you should have at some point studied is that a rational number can be written as a decimal in one of two ways. Folks, what I wish is that you've been through 10 and 20 with me at this point, because your background right now is sucking air real fast. Okay, what do we mean by a decimal when we talk about a rational? What two kinds of decimals can we have? Repeating or non-repeating, called terminating. The terminator. Give me an example of a terminating decimal. Terminating decimal, a decimal that ends. Okay, 1.2. Another one.
0.3.
0.23.
0.3. Another one. You are wanting that number in front of the decimal, aren't you? 6.2. How about 0.25? 0.75. 0.10. All terminating decimals. Give me a repeating decimal. 0.3 forever. 0.3 ad nauseum.
0.13.
0.1333. 0.66666666. 2/3 can be written as point with 6 forever. Right? Those are all rational numbers. So what is an irrational as a decimal? Be careful. What was talked about here as a rational was 0.33 forever. And one way of doing that is putting the little line over the 3 and let it go forever.
Okay.
So that's still rational. But an irrational, what does it then tell us? Can it be terminating? You just told me if a decimal was terminating, that terminated, stopped, as an expansion, it was rational. So if it's irrational, it can't terminate. Can it repeat?
No.
No. Can't be a repeating decimal. So it's non-repeating, non-terminating. Like pi is irrational. How many rationals do we have? An infinite number. There's no end to them. You can just see the tail end of infinity there. And how many irrationals do we have? It turns out infinitely many also. So two different groups, sets, rationals and irrationals. We talked about whole numbers. That's like your counting numbers, but includes 0. And we talked about the integers. Now you need to have that as part of your background. So one of the things you've got to spend some time doing tonight, you've got to work with what it means to be a rational, irrational, integer, whole number, real number. And there's a neat diagram that I'm going to go to now in your book, which visually may help you reflect on what we're talking about, and it's on page 30. I'll get that so we can see it here. Page 30, here's a neat diagram. As soon as I get it in focus, I need to darken it. Let's try that, Debbie. There's a diagram on page 30. Looks like nested rectangles. But notice you have the natural numbers. 1, 2, 3, 4, 5, the positive counting numbers. We call them natural numbers. Then the whole numbers include 0, so you add that into it. Then you add the negatives of all the whole numbers, and you get the integers. And then you take the rationals, and that's the whole left side. And then on the right side, you have the irrationals. And the whole box together is called the reals. Neat question in a test. Draw a diagram that represents the subsets of the real number system. It appeals to the artistic side. You should be able to do that. Okay? What about the real numbers in a graphical presentation? We talk about a number line, and that you can then put the numbers on the number line. Now, there is an effort here on page 31 to show you a number line. A little bit of a misrepresentation because it looks like the only points in the number line are what? Integers. But what you're guaranteed is at any point on that line is related to a real number. And vice versa, any real number, you can be located on the number line, the real number line. Now, all the way back to Math 10 and in Math 20, you have an opportunity to talk about graphene. I didn't say graphene. Think caffeine, graphene. Really upsets me when you say graph, when you mean graph, no T. So think of caffeine, graphene, and you have a horizontal axis and a vertical axis. Those are just number lines with real numbers on both. Part of the notation that is involved in this subsection, and we're talking about section 1.4, involves some important notation of the type of focus I've had a little bit earlier. Here's a rather important one, and of course the usual effort, and I'm trying to get that, all this neat effort of having color in the textbooks does not translate well into document cams. Let's try going to the, that is on page 32. This is called the double negative. So you have the inverse of x. The inverse of x is x. Now in English, you know that as the double negative. I don't got none. Now we have managed to get so sloppy in language that doesn't sometimes translate. People think, well, gee, that sounds good, which in days gone by would have been not allowed as appropriate rhetoric and would have been marked as some kind of error in writing a paper. But it's important for you to realize that the negative of 3 is 3. Let me write that over here on the right side for a moment, Debbie. If I have the negative of 3, that's the double negative. So that says you want the additive inverse of the additive inverse of 3. That gives you 3. Now there is a very important issue brought up here that may be misleading to you. When you see the letter X with a minus sign in front of it, your assumption may be that it's what? That X itself is positive. Not necessarily so. This does allow for the additive inverse of the additive inverse of the additive inverse of 2. That is what this allows for. So what's this answer going to be? A negative 2. So what do you tend to do? Count the number of negatives. And if it's an odd number of negatives, then you say, aha, my answer is negative. Thank you for the tweaking. Okay? Back to the document cam. Although the page looks pretty messed up with some keystoning there, let me flatten the page as we're looking at it. That's okay, Debbie. Now let's go to it. That's a very important statement that we're going to have. Now, related to this idea is something that may be new to you a little bit more so than would be the case, the absolute value. And again, I guess I better darken that a little bit. That reads a little bit better. I don't know which monitor is giving the better read on it. But this is the absolute value of a number, the absolute value of x. So most of you think of signed numbers. When I talk about a -2, you think, well, that's a signed number. 2 is the usual way we write a number. -2 would be a signed number. If you think of where you would place a number on the number line, 2 would be to the right of the origin. So I'm going to go to the number line we see here on page 32. So what I'm looking at on figure 11, page 32, the 2 would be right there where I'm pointing. That would be a positive 2. So where would you locate -2? The other side, correct? That's -2. Now the question, what does the absolute value of -2 represent? Well, if -2 is right there, the absolute value of -2 says what is the distance from 0 without regard to whether you're right or left? It's going to be 2. So if I want to write that statement in symbolic notation, and I'm going to again come to the right side over here, I think of the absolute value of -2 being 2. Now some of you may think, well, we just throw the sign away. But the question as we do this, and Debbie, what I'm going to need to do in a moment is migrate over to the side there. And so I'm going to be about where the chair is. If you can just move the chair for a moment, and I'll be using that as my location at the board. But as we talk about the absolute value of a letter, where we don't know what the letter represents, we have to be careful. Now this next definition turns out to be one of those little areas where you can get tripped up very quickly and is very important. Okay, and it will be on the test, just about guaranteed. I try to find those little points that I think are important and make sure you remember them. We're going to talk about the absolute value of a letter. So what I'm going to do, Debbie, is just pan with me as we come back now to the board, or not the board, but over here to the book. Let's look at the absolute value and what it says. Because the point here is I don't know what x represents. I'm just saying I want the absolute value of x, and what I have here then is vertical lines around the x. I put it in jail. Now, I want to know what the answer is going to be. Well, if x itself is positive or 0, it's just the number inside. That's what this is telling you. So the absolute value of 2 is just 2. Now, question. What happens if x is less than 0, like a -2? Then it says I'm going to take the inverse of x. So if x is less than 0, like -2, and Debbie, what I'm going to ask you to do is go to the absolute value of -2 I have on the board, and just click to that when you get a chance. So we were looking at the absolute value of -2, and we're going to flip-flop back and forth here in a moment. Okay, whenever you're ready, I'll let you go with it. Oh, okay, you're going to out the other camera. I was just going to let you go with one camera. Okay, as we go to the absolute value of -2, understand while we leave it there that that is the same as negative a -2 because of what? This double negative we talked about. So let's come back to the document cam. There is my negative of x where x itself was less than 0. So with that in mind, what we are going to do is again be in a position to write the absolute value of x. So as we come to the sideboard, if I ask you to give me the definition for the absolute value of x, you write it's equal to x if x is greater than or equal to 0, and it's equal to minus x if x is less than 0. And as I say, this becomes one of the areas in algebra that bothers people. Reason? It's very simple. When you see x, you think what? A positive, because you don't see any sign there. Just like when yesterday I asked you to give me a number, in your head was what? A counting number. A natural number. So when you see x, you have to understand that x can be negative even though there's nothing in front of the x. Now that's perhaps the most critical point of the semester already, because if when you see x, you cannot in your mind allow x to be negative because you don't see the negative sign, then it tells me that you have some fixations that are going to cause you trouble that'll be a problem in algebra. It's one of the transitions from arithmetic to algebra that's very critical, that you are able to think of x as representing a negative number, and when we say number, it can be something other than a natural number or counting number. Now, with what we've talked about today, language is very, very critical. Extremely critical. Now, I'm going to go ahead and hit some material from arithmetic that's part of the review process here called prime factoring, and how we use it to find common denominators when we add fractions, and how we use prime factoring to reduce fractions. It's part of Math 10. First, it is expected as a background in 20 and is supposed to be part of your background here, so I'm not going to belabor it very far. But I'm going to look at two fractions I want to add, 5 over 36 and 7 over 48. Now, it goes without saying that these are common fractions. They involve a numerator and a denominator. They are proper fractions, and all that is vocabulary that you are supposed to recall. I want to factor 36 and 48 into a product of primes. The prime numbers are supposed to be familiar. The list of primes, 2, 3, 5, 7, 11, 13, 17, 19, and so on, they never end. We start writing something like 36 as a product of primes by dividing by the first prime, 2, getting an 18 using short division, continue the process, getting a 9, going to the next prime, a 3, we continue until we get a 1. That is not something that I want to, again, push too far. It's part of your background. That means I can then write 36 as 2 to the second and 3 to the second. Writing a composite number as a product of primes using exponents. Every Math 10 student coming out of Math 10 does that blindfolded nearly. Now the 48, again, I divide by the 2, get 24, divide by the 2, get 12, divide by the 2, get 6, divide by the 2, get 3, divide by the 3, get 1. And you should be able to do those divisions as fast as I was writing them at this point coming into an algebra class. If you can't, you're ill-prepared. 48 as a product of primes using exponents. How many 2's do I have in the product? 4. So I write 2 to the 4th, 3 to the 1st. Then you want the LCD, the least common denominator. That tells you that you have 2's and 3's, and then you take the what? Well, what exponent do I choose? This is the crucial part. The larger of the exponents. So when I had 2 to the second and 2 to the 4th, I use a 4. When I had 3 to the 1st and 3 to the 2nd, I use 2. So my LCD is 2 to the 4th, 3 to the 2nd, which is 16 times 9, which is 144. That's part of the background you're supposed to have today or yesterday. So now I'm going to rewrite each fraction with a new denominator. So I will now slide to the left. And as we do that, I'm going to write up here this now as 144 and this as 144. From your arithmetic background, irrespective of when it was, most of you would divide 36 into here to find out how many times 36 go into 144, and then multiply that answer times the 5, right? And you take 48 into 144 and get a number and multiply that by the 7. But we aren't going to do that because we're going to do some pre-algebra with the kind of thing you'll be doing in here as we do what is called factoring, just like prime factoring. Well, as I look at these numbers, let's come back and see what we have with these two products and what we wanted in the LCD. Here was my 36. It was 2 to the second, 3 to the second. And what should my LCD be? 2 to the fourth, 3 to the third. So what am I missing here that's down here? This is called compare now. 2 to the second, 2 to the fourth. I'm missing what? 2 2's. That says I have 4 2's. This says I have 2 2's. I need 2 2's, which is 4. So if I multiplied this by 2 to the second, I get this. Okay, slide back to the left. That's where this 4 comes from. And I use the basic principle of fractions, which said if I multiplied the numerator, or I should say the denominator by 4, I should multiply the numerator by 4. Hence, I get 20 here. Okay, same idea. Sliding back to the right. Here is my 48. Here's what I wanted. What am I missing? I have 4 2's. 4 2's. That's good. Remember, the exponent tells you how many 2's are in the product. So that means you have 2 times 2 times 2 times 2. Here I only have a 3 written once. Here I have it twice, so I need a 3. If I multiplied this by 3, I'd have my LCD. Sliding back. That's where this 3 came from, and 3 times 7 is 21. We add the 2, we get 41 over 144. But if you were in a Math 10 with me, you wouldn't be allowed to do that. You would be asked to do this as an intermediate step and say I have 20 plus 21 over 144, and then write 41 over 144. Then you'd reduce it if necessary. Why do you know this does not need to be reduced? 41 happens to be prime. And 144, as a product, involved 2's and 3's, not a 41. Now this intermediate step is very critical. Okay? If I have two fractions in a symbolic representation, let me slide just a little bit more, A over C added to B over C, and by the way, this is the way we write fractions more commonly in algebra rather than the vertical presentation I had here, write them horizontally, but this says the denominator is the same. If the denominator is the same, what am I supposed to do? Add the numerators, and here's my intermediate step, A plus B over C, which is exactly the intermediate step I represented here. So in a pre-algebra or a Math 10, I go through this step to facilitate a general statement that you should be comfortable in writing. How do we reduce fractions using primes? Well, we'll slide over to the right again. And I realize this is being done quickly because it's not supposed to be new. This is part of your background coming into this course. And if you don't have the background, spend time working maybe 3 hours a day in homework rather than an hour or 2 hours a day getting caught up for the things you should have as a background. Now, 36 over 48, I want to reduce it. Most of you are familiar with the canceling concept. I'm not going to use it here. I'm instead going to write my 36 using these primes that I had. But I'm not going to do it with exponents. I'm just going to write 2, 2, 3, 3 multiplied together. Then I'm going to write my 48, which involved 4 2s. So that's 2 times 2 times 2 times 2 times 3. Now search and destroy. If you see a 2 up in the numerator and the denominator, you can destroy it. Cancel out and leave 1s. Then I see what? Another 2. I see a 3 and a 3 down here. So what's left in the numerator? A 3. What's left in the denominator? 2 2s, which would give me 4, so this reduced to 3/4. Now I know that you could have argued immediately 12 goes into here 3, 12 goes into here 4, hence 3/4. But you are going to have to do prime factoring in algebra to do the same kinds of reduction of a fraction, hence you need the background I just went through here. So I'll leave that on the board for a moment as I go ahead and return to the front. Now, what we've been talking about is section 1.1 and 1.2 of your text. My goal by tomorrow is to finish chapter 1. It's all review content. I will recap a little bit on Thursday, and then Friday we're in chapter 2. Moving right along, having fun. Just a reminder that in chapter 1, we are dealing with, in section 1.1, a review of fractions. And if we look at the kind of statement I just did a moment ago, let's see if I can find that now. I want the statement. As life would have it, the author used the letters in a different way. Let's go to page 5. A over B and C over B. I was sure it was going to be A over C and B over C, but it's the same basic statement. And then the answer, if you add them together, using my infamous technological version of scrolling, moving the book, that's the same statement we just had on the sideboard. And the same kind of thing is done on other portions of this section in 1.1. The process that I just went through in doing LCDs is summarized for you in 2 steps to happiness on page 6. Top of the page, where you have fractions with different denominators, and the idea that you factor both denominators, and then you find the LCD and proceed as I did on the sideboard. You should be comfortable with everything in section 1.1. We've done that today. The homework in that section is going to be 1 through 62 odd. Make sure that that does what I want. Yes, 1 through 62 odd in section 1.1. Now, we haven't talked about order of operations. I have wanted to do that today, and symbols of inequality and equality. But we did do section 1.4 on the real numbers. And so the work there for homework in section 1.4, page 34 and 35, is 1 through 14 all. So let me write that on the board for you so you can see it. And what we will do, I guess, Debbie, if you want to just run camera 2 over to the sideboard in the space I have in the right, you'll make that transition, and I'll walk over there in a moment. And the homework now, as we come over here to the side, is going to be, again, this is on pages 34 and 35, and you have 1 through 14, the TH means through, 1 through 14 all, and then the homework also was on page 9 and 10, and that was 1 through 62 odd. And I didn't get everything I wanted to do today because I had a whole section of problems that were going to be in order of operations. Now, my goal is to go ahead and cover Probably tomorrow, I'm thinking in terms of 1.5, 1.6, and 1.2, about 3 sections of material. Folks, this week, while things are light, this is called semester light, Bud Light, semester light, that kind of thing. Give me 2 or 3 hours in review and try to pull yourself up by your bootstraps, covering the things in pre-algebra and math 10 that should be part of your background. If you don't take care of them now, they are going to come back and haunt you, and your problems will be in arithmetic, not so much algebra. You've got to take care of those gaps. Now, I had a homework assignment. I'd hoped to answer some questions on it. Just didn't have time. I'm going to collect it. Make sure you have your name on it, fold it in half lengthwise, and you're going to turn that in to me, and I'll get it back to you tomorrow, and then we'll just talk about some problems on it. I spent a lot longer covering the properties of the real numbers than I thought. Debbie, we're going to close with Rod Stewart, and what's your choice?
Stay with me.
You got it. Stay with me through algebra. Have a great day.